Hi, my name is Anthony Alvarado, and I am with Ayres Associates, and I have been in our industry and a part of Ayres for over 20 years now. With me today is also Steve Griffin.
Thanks, Anthony. My name is Steve Griffin. I am one of our hydraulic engineers for the Colorado Department of Transportation, and I represent Region 4. And I've been doing hydraulic engineering in some capacity for about 15 years. So I will start us off with today's presentation, and then Anthony will pick up. So a quick lay of the land for our next few minutes together. We'll spend a brief time outlining just what a two-dimensional model is, their advantages and challenges. From there, we'd like to transition to what we as an agency are noticing with these models. We function here in Region 4 both as modelers and as clients, receiving these models as deliverables from our consultant teams. Now that this technology is becoming more widely available and used, we're starting to see trends when we see these when we QC these models. So it might be instructive and helpful to highlight some of those today. We'll then conclude our time together with Anthony describing a recent project that Ayres designed for CDOT Region 4, which is a bridge replacement out in Ray, which of course that area of the state just had a flooding event in early July, so this is particularly timely. Many of you may be familiar with CDOT's engineering regions. Region 4, as you can see on your screen, covers quite a bit of ground. Not as much as our friend Stuart Gardner covers for us out in Region 3, but pretty close. The site that we'll be talking about in a few minutes with Anthony, Ray, is out in Yuma County on the far northeastern part of the map near the Nebraska border, for those of you not familiar. Now, for those especially interested in the progression of our field, hydraulic modeling in particular, this is a handy reference from Federal Highway's October 2019 manual, which is entitled Two-Dimensional Hydraulic Modeling for Highways in the River Environment. And this is, of course, available now on Federal Highway's website, free of course. One detail I might add to this, which is numerical modeling in hydraulics, really ramped up in the 1960s with the advent of smaller, more powerful computers that were housed in universities. And later, of course, we have the home computing version. So you see on your screen HDS1, HEC2, WizPro, etc. These are all one-dimensional hydraulic models. So briefly, what do we mean by a two-dimensional model? Well, a one-dimensional model is solving its governing equations in one direction. So a 1D model uses average velocity for the entire cross-section. And that velocity is in the direction of flow downstream. A two-dimensional model is capable of solving its governing equations in two directions, though it's still depth averaged. So we're not getting the velocity profile as one progresses from the bottom of the channel to the top. That would be a 3D model. You see here some key differences between 1D and 2D modeling. Whereas the model and the user are by necessity making a number of assumptions in 1D space. In 2D space, we're able to rely more on our actual data to make computations based on our governing equations. Now, this is not to say that 1D models don't have their usefulness. They absolutely do. But 2D is quickly becoming the standard for much hydraulic design by practitioners. So here's what we're seeing. SRH2D, HEC-RAS 5.0, and other two-dimensional models have really exploded into our field in the past 5 to 10 years, to where now we more or less consider them the standard for design for many hydraulic projects. You could think of bridge replacements, river rehabilitation, sediment transport, we could go on. So we've got this new technology with new users. And a lot of 2D modeling is being performed by newer staff. This might be one of their very first hydraulic models out of their career. Or it might be a more experienced hydraulic engineer who is very good with the 1D environment and is now learning 2D for the first time. So now add to that, we have clients or regulatory agencies who are also getting up to speed with this technology. Maybe we as an agency have a checklist for our QC of a 1D model, but not for 2D. Do I, as a reviewer, know how to manipulate that model? Do I know the common pitfalls? Can I tell, as a reviewer, if a stable solution was ever reached? So, a new technology with new users and new reviewers. What could go wrong? Well, indeed, what could go wrong? Well, plenty could go wrong. These might be pitfalls similar to those that we find in a one-dimensional modeling space, or they might be unique to a more complex modeling environment like 2D space. These might be abnormalities in our topographic surface. They might be a mesh network that is too tight or too loose. It might be an inappropriate time step. It might be a hydraulic structure. But whoops, we forgot to model the pier. Since 2015, that's when I took the NHI course in SRH2D. I have personally created somewhere around 40 two-dimensional hydraulic models. So in my office, we also have an EIT, Phoebe, who has created several models of her own. We've had a number of interns over the past few years who've made their own models. And many of you listening today are building quite an impressive resume of modeling projects in 2 dimensions. I point this out only to say that as modelers, each of us has fallen into some common pitfalls with our modeling. So we wanted a way to catalog these pitfalls as they come up and to start checking for these with our new efforts. We also function in my office as reviewers. We're getting more and more 2-dimensional models as a client. And to that end, some of the same pitfalls that we are conscious of in our own modeling, we're also seeing in deliverables we receive. And this is all understandable, right? This is a new technology for many of us. So what we've done, and you can see on the screen here, is we've come up with a QC checklist. We use this internally here in the region. We also have begun including this checklist in our scope of work when we bring on a consultant team to work alongside us to perform hydraulic modeling. In those cases, the idea moving forward is that these models will be QC'd by the firm internal to their own organization before reaching the client's reviewer. This checklist is rather comprehensive, and the idea is not to nitpick hydraulic models into oblivion. That doesn't help us, that doesn't help our consultant team succeed. One of the things a spreadsheet like this accomplishes for us is it establishes a common expectation of quality of the models we're building and the models we're reviewing. So what are some of the items on this checklist? And we'll go through these fairly quickly. Well, each item on the checklist is here because at some point we built or received a model that struggled with this particular feature. So we'll begin with boundary conditions. Similar to 1D space, we need to be sure that our upstream boundary condition is located far enough upstream from our area of interest. In 2D space, we've been seeing the flow, we've seen all kinds of scenarios. We've seen the flow injected on the side of a bluff. We've seen convergence issues caused by too coarse or too fine of element spacing. The same with downstream boundary conditions. We've found that the orientation of elements at the downstream can also be the source of instabilities. Naturally, we're checking roughness values. In 2D space, roughness can now be represented with polygons, as you see here. Making sure that the channel and overbank roughness corresponds to accepted values, that's something we're checking. There continues to be a discussion on how 2-dimensional Manning values might differ from 1-dimensional values. That does not appear on our QC checklist at this time because discussion is still ongoing to that point. The biggest issue we're finding with terrain that is being used for these models is where 2 or more sources are merged together. So you could think of a LiDAR source with ground survey being merged together to form a single cohesive surface. And from time to time, we will find discontinuities in these surfaces, so ridges and valleys that don't actually exist in real life. Sometimes we find that a lack of break lines in the surface can cause irregularities that aren't really there. A lot of these issues are easily solved, but of course, this is the data underlying your mesh. So if the topography has got instabilities or things that aren't there in real life, the mesh is gonna replicate that. We also have several items that check the quality of the mesh itself. Again, we don't have nearly enough time to go into mesh development today, but I'll just say that the biggest things that we're seeing are with the Courant number being larger than 1. So what that means is, if you're not familiar with that, either the mesh is too tight or the time step is too large, or it might be a combination. So what that results in is elements in the model are getting skipped, which can result in a bad run, and it can definitely result in instabilities. Also, ideally, we are making holes in the mesh for certain features, as you see here, like a building or an insurable structure. Now, as far as hydraulic structures, we have been seeing lots of modelers forgetting to represent features like piers for bridges, which obviously are critical features. It can also be quite difficult to appropriately represent abutments and some steeper roadway embankments in your mesh. We also need to make sure that we're capturing the high point of the road and other hydraulic controls in the topography. Pressurized bridges and culverts present their own unique challenges, so we've got items to check on our sheet with regards to these features. And ultimately, we're looking for those output files that tell the modeler and tell the reviewer, is this model actually converging on a solution? I would have to say that more models than not show up in our office without these really important output files. Monitor lines, HY8 output, if you've got a culvert, monitor points, something called the INF file, which helps us figure out if the model is converging on a final solution. Now, these files are automatically generated when the model's running, so you can open them in real time during the simulation, see how your model's performing. They also help with debugging, isolating those areas of the mesh that might be having trouble converging on a solution. There are some resources I would point you to here as a final note before we hand it off to Anthony with a case study on this QC checklist. Certainly we have the checklist itself. You are welcome to contact me by email or phone, and I can get that checklist to you. Federal Highways has also come up with a similar checklist, and that's freely available at the Federal Highway Hydraulics website. There is also the NHI course that Federal Highways puts on through NHI, and the course number you see there listed on your screen. And finally, if you're not already doing this, I would highly encourage participation in Scott Hogan's bi-monthly webinars. They're roughly bi-monthly. And I've given the web address there that you can look into that. If you've got Scott Hogan's email, also feel free to email him. But that'll kind of give you some much more detail than what I've gone into today on some of these items. I'm going to hand it over to Anthony now, and he's going to go through a case study of this bridge in Ray where we use this checklist.
Thanks, Steve. So our case study is the bridge replacement for D-27-G, which was a timber bridge out by Ray, Colorado, kind of the eastern part of the state, like Steve pointed out. CDOT is in the process of replacing a lot of these bridges, and there are quite a few of them on the eastern plain. The assumed design for the new bridge was a two-span bridge. Just a quick reminder of where Ray is. You can see it's relatively far east of Denver and Fort Collins. It's about a 3-hour drive from the Front Range. The red dot is where D-27-G is. The green dots are actually two other bridge replacements that are happening concurrently. So the construction of all three of these bridges is happening right now. Here is a good picture of the existing conditions. So we built our 2D model. We started on this bridge. We collected LiDAR for this area. If you were to do this now, you actually wouldn't need to collect new LiDAR because there's now state LiDAR available for this part of the state, which is fantastic. This is the 500-year event. The bridge is kind of that hot spot where there's more red, more to the west. And then the other areas are where US34 gets overtopped. So we built this model, and we zoom in, and you can see the existing conditions. It's 3 24-foot spans, timber wall piers. So we finished our initial analysis of this bridge in 2D. We also checked it in 1D in regard to the floodplain regulations and the rise conditions. But we then submitted, our 2D model and our initial report to CDOT, to Steve and Phoebe, to review. And they used the checklist and then walked through their review of our bridge model. And they had some good things that they caught. So there was some back and forth on the question of the terrain data. There were some minor mesh quality issues. Another key thing they found was our model extents didn't quite extend far enough. We had a few points on the edges, but still potentially impacting where we needed to extend our model because the water was hitting the edge of it. We kind of resolved some roughness questions to be on the same page. And one critical thing that they found was that our simulation time was not sufficient. So we had actually only run it for 2.5 hours, and it did not catch all of the overtopping in the 500-year event. And you can see that in the two figures where there is additional overtopping even at 5 hours that at 2.5 hours we did not catch. So, and they had recommendations for additional monitoring lines. So it was a good process. They caught some things that maybe weren't huge impacts at the bridge location itself, but were still informative in terms of what's going on overall. And we then made those corrections and moved on to really pin down the proposed design. So when we did that, we ran 112 two-span bridge, 112-foot two-span bridge that CDOT Staff Bridge provided the concept for. Our model passed the checklist, no adverse impact, no rises of issue. Looks great. So now we get into why the 2D model. Well, what does this show? If you look at the figure, what is going on? What might be something we should take a closer look at for this bridge? Well, if you can see with the color difference, that blue area to the east side of the bridge opening, east of the piers, is an eddy. It's essentially ineffective flow through that eastern side. And that ineffective flow means that that side, that span, is not really adding any additional conveyance to this bridge opening. So we saw that. We had some internal discussions, discussed it with CDOT, and we started moving ahead. Well, let's trim this bridge opening. Can we just move it in from the eastern side and cut it? And we did. We looked at a 60-foot, 80-foot, and just a minor tweak at 100-foot, and we found that the 80-foot was best. Still conveyed the needed flow, much better than the timber bridge, hitting the freeboard requirements. Everything looked good, no adverse impact, except an 80-foot versus a two-span 112-foot bridge is nearly $500,000 lower cost, around $400,000, which is a huge win. And if you look at what we saw in the original run, it's not something that would be easy to catch in a 1D model. Even if you ran a flow distribution across the opening, you might see lower velocity over there, but you're not going to be able to tell that it's an eddy, right? Because ineffective flow in a 1D model is dictated by the user. Whereas the 2D model here, it can tell you where that is. You don't dictate the ineffective flow areas. So it was huge in terms of the design because we realized we could go with a significantly smaller bridge. And maybe 32 feet doesn't feel that significant, but $400,000 is a lot of money in terms of construction cost. So in summary, the review checklist has a few goals. And really a lot of it is to put us on the same page, us as consultants on the same page with CDOT. And with this review checklist, you should see this and take this into account at the scoping phase. If you're doing a bridge replacement, something where that's going to involve 2D modeling, that's when the review checklist should really start to come into play. And it should be used internally first as part of your own QA. That would be the goal. Then you could then submit it with your model to CDOT, and that review process will go significantly smoother. The expectations are clear. It's going to lead to less mistakes and less heartache in terms of what actually defines what a good 2D model is. And in the long run, this is going to save money in a couple ways. It saves Steve and Phoebe and CDOT Hydraulics Region 4 time It saves review time, and it'll allow us to use 2D models more and more to save overall cost on construction, which is what our case study showed. With that, we'd like to thank you for your time and open it up for questions.